Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion related to the course Introduction to Electronics. And in the last lecture, we had seen how one could build amplifiers using an ideal transistor and also with some three-terminal devices which had some non-idealities in them. And we saw how we could correct for those non-idealities and use those devices to amplify. So today, let's look at two common transistors. One of them is a bipolar junction transistor, and the other one is a metal oxide semiconductor field effect transistor, in short, MOSFET. All right, so we had seen that when we are looking at a transistor, we are looking at a property that the output current, so transistor, let's say, it has at least three terminals. There are transistors, for example, MOSFET has four terminals, but at least three terminals have to be there. Across one pair of terminals you apply input, and across another pair of terminals you take the output. So transistor exhibits this property that the output current is much more sensitive to the input voltage as compared to the sensitivity of output current to the output voltage itself. And the sensitivity of output current to input voltage is what we call as transconductance. So transistors exhibit transconductance as their prominent property, or transresistance as their prominent property, and hence the name called transistor here. And so ideal transistor, we said, is we had discussed in last couple of lectures that when we look at it from the input side, it appears as if it's an open circuit. And I0 doesn't have any dependence on V0. I0 only depends on the input voltage, and the dependence is linear. If you want to make an amplifier, the amplifier is a linear device. So I0 is simply equal to GMVI, a dependent current source here. So graphically, we can represent that I0 is independent of V0 and depends on the values of different values of input that have been applied. And I0 is linearly related to input voltage. So that's the kind of ideal characteristics, ideal transistor that we can think of. And once you have this ideal transistor, then it's very easy to construct an amplifier. All you need to do is, when you have this ideal transistor, connect the source, the signal that you want to be amplified, and connect a load here. And we had seen that it's easy to analyze. You can remove this three-terminal device and instead put this particular model here. So you get this particular circuit, and it's easy to see that the voltage gain ratio of output voltage to input signal voltage is minus GMRL. And if you choose RL properly, GMRL properly, you'll get a value which is greater than 1, and you'll get voltage gain. And not only voltage gain, you get power gain also, because the input does not draw any power from the signal source here, while output, of course, power is delivered to RL. So there's a power gain also. And we had seen that in reality, we don't have a ideal transistor like that, but we may have devices which may look like this here, that I0 is some nonlinear function of Vi, and below a certain threshold point here, threshold voltage here, the current is 0 or negligible here. So that kind of a non-ideality is there. And then I0 versus V0 also is not a constant over the entire voltage range here. It exhibits a constant current kind of a characteristics only after a certain voltage here. And we had seen that if you have non-idealities like this, we can then also we can build an amplifier where we use the concept of biasing to push the transistor into a region like this and into a region like this where it's capable of amplification. And also we need capacitors to block the DC, and capacitors to enable us to apply this signal to the input here. And also we had added this particular resistor to correct for any strong sensitivity of the circuit to resistors and supply voltages because of sharp characteristics here. All right, so as we discussed, let's look at the real transistors now. So bipolar junction transistor is one of them, and it's called, it has two junctions here, as you can see here. There are two PN junctions, one junction here between emitter and base. So three terminals are there, emitter, base, and collector. Three different regions are there, N, P, and N. There are two junctions here. One junction here, emitter base junction, PN junction, and another junction here, which is also a PN junction between base and collector here. So bipolar junction. Two junctions are there. And this is the symbol that we use here, base, collector, and emitter. And we can also have a complementary structure where N and P are reversed. So you have emitter, which is p-type, base, which is n-type, and collector, which is p-type here. So you have PNP transistor, and the symbol that we use is with the arrow going in here. Okay, no, the arrow sort of represents the direction of the PN junction here. So from emitter to base, the PN junction points in this direction here. So that's where the arrow is here. Okay. Now, although we draw a NPN transistor, so let's focus on NPN transistor. Although we draw an NPN transistor like this, it appears as if it's a bar with N and P and N. The actual structure of a transistor is more like this here, where you have, we have seen earlier that you make all the transistors and integrated circuits on a crystalline piece of silicon, a silicon wafer here. So let's say you have a silicon wafer which is p-type doped, and then what you do is in this particular wafer here, you diffuse n-type impurity and then p-type impurity and then a heavy impurity n plus here. And so this is the n-type, this is the p-type, and then this has become n-type, and there is an n plus region here to provide a low resistance path to the contacts here. So all the contacts are at the top, emitter, base, and collector here. So this makes a contact with the p region, this makes a contact to the n region here. And so transistor is more looks more like this here. And when we draw a bar like this here, is basically what we are drawing is a simplified structure between the dotted lines here. So we are drawing this n here and p here and n here, and we are also sort of ignoring any n plus and all that that is there here. So a simplified schematic NPN, but this is a more realistic structure of a bipolar transistor. And all these, so note that we start off with the p-type semiconductor and then we diffuse or implant impurities in them. We implant n-type, so this particular region will become n, and then we implant p-type or diffuse p-type, it becomes p, and then a heavily doped emitter region here. And some of the doping concentrations are given. So emitter is the most heavily doped layer here, 10 to the power 19 centimeter cube. Base doping is about, these things vary from transistor to transistor. And these are, just to get a feel for what kind of values may be there. Base doping of 10 power 17, collector doping of 10 power 16 here. Note that emitter, the thickness of the emitter here, the depth of the emitter here is about 1000 angstrom. The base width that you see here may be about 2000 angstrom. The lateral dimensions are also, they vary a lot. Let's say the lateral dimensions are the length of the emitter here. That could be 1 micron. Also note that when we see a structure like this and when we write NPN, it seems that the bipolar transistor is symmetric, that I can change emitter and collector. But when you see from here, you note that the emitter is much more heavily doped N plus as compared to collector. So the two regions are not, the transistor is not symmetrical. And note that the emitter region is over here, the collector is a much larger region that you see here. Okay, so the two are not reversible. You cannot just simply interchange emitter and collector and expect the transistor to remain the same. The emitter has a well-defined region here with very heavy doping, and collector has very light doping here, and that has consequences for current gain and other properties, breakdown voltages, all those other things depend on doping. All right, so as I said, is basically when we are drawing that simplified structure, we are looking at this thing between the dotted line, which you see over here. And also here, what we do is we sort of ignore this N plus here, because the role of N plus is nothing but, as we will see, the electrons are injected from emitter, they reach the collector. And the role of N plus is to provide a low resistance path to the contact here. N plus here, and P is the starting substrate here. So we ignore N plus and P, and we remove it and we put a collector contact here. Note that the collector contact is actually here, but then this is connected through a low resistance part to this particular region here. So we put it over here. And note that base contact, we say it is over here, but note that base contact is over here. Again, the base is connected through a small resistance to this particular region here. Okay, so instead of drawing like this, we just put a contact over here. But note that the actual contact is over here. Okay. All right, this is the top view. If you look at it, that the previous one is a cross-sectional view, and this one is the top view here. So this is the region here, emitter. This is the region here, base. This is the region here, which is the collector. And normally what we would do is, these regions are very small in size. So we have these metal lines going here, metal lines in a metal pad, another metal lines in a metal pad here. And there are maybe a very fine wire is attached to this, to the collector terminal, to the base terminal, and to the emitter terminal. And these wires, they eventually go and attach to the pins of the package that is there here. So the whole thing is put in a package, and these are attached to the pins of the package. So when you go to the lab and you look at a transistor, you'll see that the bipolar transistor has three pins, emitter, base, and collector. And inside it would be, if you open it, inside would be a small piece of semiconductor which is attached through these wires to the pins of the package that is there. So let's see how this bipolar transistor works. So we've seen earlier that when we take a PN junction, NP junction here, and when we forward bias it, so note that N type is made negative, P is ground here, so N type is made negative, so you're forward biasing the PN junction. And when you forward bias it, you inject electrons. So this red shows you're injecting electrons into the P-type region. And you're injecting holes from P to N region here. Now we are considering a special, and so the net current which will flow here in this particular one will be a current due to electrons and a current due to holes. Note that the electrons are flowing in this direction, so the current through them is also in from right to left here. So the two currents add up. There's an electron current and there's a hole current here. And both of these currents is a PN junction diode. So both of these component currents are exponentially dependent on the voltage that we apply here, the forward bias voltage here. Now, what we are going to do is consider a case where this is emitter and this is like a base, and emitter is much more heavily doped as compared to the base here. So what happens is this electron component becomes much larger than the whole current component here. So for the sake of discussion, keep in your mind that the junction is constructed in such a way that the electron current maybe is about 100 times, let's say, the whole current here. And that's why just for that sake, the electron current is shown as a thick line, showing that is a lot more in magnitude as compared to the whole current here. So keep in mind roughly that electron current is about 100 times the whole current here. And that's because this region is made much more heavily doped as compared to the base here. All right, so let's say, so that's why we made it N plus here, plus showing heavy doping here. And of course, at the junction we saw earlier, there's a depletion region, all that is there here. And so this is now our emitter, this is our base. And note that it is, we are forward biasing the emitter. So electrons are injected into the base and holes are injected from base into the emitter here. So that's what is happening here. So what we're going to do is try to construct a transistor by bringing two PN junctions. It's a bipolar transistor with two junctions. So we're going to bring two PN junctions together and then see what happens here. So I equal to IN plus IP, and we said that IN is about 100 times IP here. Okay. Let's look at another junction here, P and N here. And in this case, the other junction, note again, there's a depletion region and all that. So this particular junction, we reverse bias it. So we apply a positive voltage to N, and P type is ground. So it's a reverse bias junction. And note that in reverse bias junction, the direction of the current has to be from N to P here, from right to left here. So you're basically asking holes to flow from N to P, and you're asking electrons to flow from P to N. And because there are very few electrons in P type, and that's why the current is very low, and there are very few holes in N type, so that's why the current is very low here. So we've shown in dotted lines that the current is very, very low. But let's focus on this current here. This is the electron component of the current. So electrons are have to flow from P to N, because that's what the supply voltage is demanding. And the current is small, not because electrons have difficulty in going from P to N region here. Note that the direction of the electric field would be in this particular direction here, from right to left here. So the electrons have no difficulty in going from P to N. The reason why the current is very small is there are very few electrons in this P region here. Okay. And further, if I change the bias here, note that the bias does not do anything to the availability of electrons here. And therefore, as I change the bias, the little current that flows here doesn't change with the bias here. Because all that the bias will do is change the electric field. But electric field has no effect on this current here. Electrons have an easy time going from P to N. That's not a problem. The problem is the availability of electrons here. So this voltage here has very little effect on the current, the electron current, or the whole current here. Okay. All right, so we have these two junctions, and this is what is happening in the forward bias junction, and this is what is happening in the reverse bias junction. Now let's bring the two junctions together here. Let's fuse them together here. So when you fuse them together here, these electrons which have come into the P region here, note that when you forward bias it, a lot of electrons come into the P region here. And now these electrons that have come into the P region here, they can then go to the other junction here. They can go like this here, because the base that you see here is made pretty thin. And so the electrons that come in here, because of forward biasing, they diffuse and they reach the other junction here, because the separation between the two junctions is maybe 100 or 200 nanometers. So it's a very thin separation, and the electrons can easily diffuse and reach the other end. And once they come here, then there's an electric field which sweeps the electron into the N region here. So the electrons are able to come here. So practically what happens is all the electrons that were injected from the emitter into the base, now almost all of them, barring a few, almost all of them travel across to the other junction, and then there's a field, and then they reach the collector region here. So this is very interesting, because note that this is a reverse bias junction. We just said it's a reverse bias junction, and in a reverse bias diode, we expect very little current to flow. But we have to keep in mind, why does very little current flow? Very little current flows because there were very few electrons in the P region. But now that we have connected a forward bias junction, so this forward bias junction injects a lot of electrons into the P region, and therefore a lot of current starts to flow here. On the other hand, this component of the current remains as it is here. So note that we said that this current, these electrons are about 100 times stronger than this particular part here. And so the net current, the electrons that are injected here, they all flow into this particular region here. So a lot of current, collector current, starts flowing into the region here. And so if this is emitter, base, and collector, so let's we'll ignore the few electrons that may recombine here. So all the electrons that are injected from the emitter, almost all of them reach the collector here. And then this is the holes which are injected from P to N. And so collector current will be practically equal to this electron current here. Practically equal to electron current. Note that there are a little bit of holes that go from N to P reverse bias current, but that's much smaller here. You can ignore it. So collector current is practically equal to this electron current here. Emitter current is made up of these two components here. Emitter current is electrons and holes here, I equal to IN plus IP here. And base current, the current that comes in from here, note that the base current, the holes are being injected from P to N. So the purpose of the base current is to supply these holes here. So the base current is IB equal to IP. And you can verify that IE plus IB plus IC, the Kirchhoff's current law is satisfied. And so collector current is IN, base current is IP. So the ratio of collector and base current is IN by IP. And we said the ratio of IN and IP is these two current components here. And because it's N plus, so this current is maybe 100 times stronger than this. So we have a current gain. We have IC by IB, which is what we call as beta, is much, much larger than 1. Maybe 100, maybe 50, maybe 150, depending on the construction of the transistor here. The other part, okay, so here what we did was we applied a forward bias here, we put it to ground, and we applied a reverse bias like this. We can do alternatively we can put emitter to ground, we can apply a voltage here. So if we apply 0.7 here, so that forward biases the emitter base junction, about 0.7. And if we apply 5 volt here, note that the net voltage across the junction is 4.3, so it's reverse bias. So we can do that, same thing happens even now here. Same operation as before. All right, and note that this current that flows here, whether you take IN or IP, these are all exponentially related to base emitter voltage. These current components come about because of the forward bias on the base emitter voltage here. So this IC, which is IN, is nothing but exponent VBE by VT here. It's a diode current, except that is flowing through this reverse bias collector base junction here. And so what is very interesting is the following. Note that we said one essential property that a transistor must have is that its output current. In this case, let's take it as the collector current is the output current. The output current should be very sensitive to the input voltage here. This is the input voltage here, right? So this that you apply to the base here. Base emitter is the input voltage here. And it should not be sensitive to the collector voltage here. So this is what we find. IC is very sensitive to the base emitter voltage here. In fact, it's an exponential relationship. IC depends, because if I change from 0.7 to 0.71, well, these current components would increase significantly because it's a forward bias diode. And forward bias diode, the current changes exponentially with voltage here. So these current components, they go increase exponentially. On the other hand, if I change this voltage here, and as we said, as you change the collector voltage, all it does is maybe increase or decrease the electric field. That doesn't do anything to the current here because it's a reverse bias junction. And electrons already have an easy time going going across from P to N. So that doesn't control current at all. So collector current is insensitive. If whether I apply 5 volt or 6 volt or 3 volt, collector current is not going to change, because collector current depends on how many electrons were injected from N to P. That is the controlling factor here. So that's how we get the transistor action. Collector current is independent or very little dependence on the collector voltage. While collector current has a lot of dependence on the input base voltage. So this was the transistor that we said an ideal transistor looks like. Our transistor, bipolar transistor, looks more like this here. If we take emitter as a common terminal, between base and emitter there's a diode. So we don't have an open circuit, we have a diode here. And between collector and emitter, note that through the collector terminal there is this current IC. But this current IC is dependent only on base voltage here. So that's why we represent it as a voltage dependent current source here. IC is a exponential relationship to VBE. So it looks like this here, except for that there is a, it's not an open circuit here. There is some resistance or some diode here. And this is a nonlinear relationship that is there here. But it's a transistor because collector current is very sensitive to base emitter voltage, but is not sensitive to collector emitter voltage. The other way of representing a transistor is not in terms of VBE and FVBE here. In terms of IC, we can also write it as between base and emitter there's a diode, and at the collector we can, instead of writing in terms of base emitter voltage, we can write it in terms of base current. And we saw that the ratio of IC and IB is beta, so we can write it in this particular form also. Beta is IC by IB here. And this current has an exponential, it's a diode, so it's an exponential relationship. And IC is beta times IB, so IC is also exponentially related to base emitter voltage. All right, so this is the characteristics, the base current versus base emitter voltage. So base emitter voltage is a diode. Collector current with respect to base emitter voltage is also diode, because collector current is nothing but the current that came from the base emitter junction here, the electrons that came from here. So it's also a diode here. And collector current with respect to collector voltage here, collector base voltage here, is a constant here because it doesn't depend on the collector voltage here. Okay, so these are my transistors characteristics here. And this is IC versus VCB. We can plot IC versus VCE also here. So IC versus VCE looks more like this here. And so IC versus VCB here. So VCE is nothing but VCB plus VBE here. And when you forward bias the base emitter junction, so this is practically constant, about 0.7 or so. So you basically, as you increase VCE, you're increasing VCB. And that's where this part of the characteristics is basically this part here. When you reduce VCE to very small value, smaller value here, then what happens is the base collector junction also gets forward biased, and we have some non-idealities here. The transistor is going into what we call as the saturation region here. So we'll not go into the details of it. If time permits, we'll see a little bit of it in the next lecture here. All right. Now, transistors are of various kinds. We just said that there's a bipolar junction transistor, and there is, of course, there's the other kind which is called the field effect transistor. Now, in field effect transistor also, there are many kinds of field effect transistors. There is a MOSFET that we are going to look at briefly in the next couple of minutes. And besides bipolar and field effect, there are other kinds of transistors also. Other kinds of field effect transistors, other kinds of transistors also. And so let's look at how the field effect transistor works. So again, keep in mind that from a transistor, what we are looking for is that the current is very sensitive to V in and not very sensitive to V naught. So that's the property that we're looking for. So what is this field effect principle? So imagine that you have an N-type semiconductor, and an N-type semiconductor will have these donor impurities that you see here in circles, and it has all these electrons that are there here. And so overall it's neutral. The impurities are fixed in place. The electrons, of course, they're mobile, they can move. So imagine now I make two contacts to it. I make a contact here and I make a contact here. And then let's make this ground and let's put this 5 volt here. So when you put 5 volt here, of course, the current will flow through this N-type semiconductor. It has electrons and current would flow. And let's suppose that we bring another plate or a contact close to the semiconductor here and attach a terminal here. Now, if you're wondering how are we going to suspend this particular electrode, well, you don't have to suspend. All that we care for is that it is separated from the semiconductor by an insulating layer. So we could have an insulator here, as we will see, a silicon dioxide or something of that kind, which separates the two here. Okay. So let's apply a negative voltage here. So when we apply a negative voltage, so think about this as one plate of a capacitor. Then you have, let's say, air or a dielectric, and this whole semiconductor acts as the other plate. And the other plate is connected to ground also, is connected here. So what will happen is, when you apply negative, you require negative charge to be on this particular metal plate here. And what it does is, note that the negative voltage here will repel the electrons from close to the surface. So these electrons that are there here, they will be repelled, they will come here and they will sit here on this plate here. And so what you've done is you've removed electrons from this particular region here. And the electrons will be first removed from close to the surface, and then electrons from deeper into the semiconductor, they will be removed gradually as you increase the voltage here. So because you have changed the number of electrons, you've reduced the number of electrons, the current which was flowing earlier would reduce because you have less electrons in the system. And therefore, what we are talking about is modulation of conductivity using electric field. The conductivity of this sample will depend on how many electrons are there in that particular sample, or how many holes are there in that sample. Because we are talking about N-type, so we are talking about electrons here. So you are modulating conductivity using electric field, and that's what we call as the field effect principle here. By applying an electrostatic field, we can alter the charge concentration here and thereby affect the conductivity and thereby affect the current. And we can also see transconductance being there. The voltage is being applied between these two pair of terminals. If we take this as a reference, the voltage is being applied between these two pairs, and is altering the current flowing between these two pairs of terminals here, right? Between these two. So the current flowing here in this particular terminal here is being controlled by voltage being applied here. So that's the transconductance feature here. And of course, we need to show here that for this to act as a transistor, the current flowing here should be very sensitive to this voltage and not very sensitive to voltage over here. Then it would act like a transistor. So this was the principle of a transistor that was first described in a patent filed in 1926 by this person called Lilienfeld here. And so he's the person who's first credited for inventing the transistor, inventing the concept of a transistor. However, he could not fabricate it, and one had to wait for another almost like more than 20 years for the first transistor to be fabricated. But this was what he described was, if you read the details of this particular patent here, what he was describing was this field effect principle, how we can control the current flowing between a pair of terminals by applying a voltage across a separate terminal here. So he was describing how one could construct a transistor. All right, so what we're going to do is look at a kind of a field effect transistor which we call as a MOSFET. And so let's look at a MOSFET which is N-type. So MOSFETs are also N-type and P-type. So let's look at a MOSFET which is N-type. And you'll see that we call these MOSFETs as enhancement mode transistor. And sometimes we also call it an inversion mode transistor. All right, so both of these meanings will become clear in a minute or a couple of minutes. So we have P-type silicon. So let's see how this may be constructed. So we start with P-type silicon. We deposit silicon dioxide on this particular surface here. You can deposit or you can heat up P-type silicon in an oxygen environment, and a part of silicon becomes oxide. All right, so on top we deposit metal here. Okay, so we deposit metal. This region, we convert it into N-type here, N+, heavily doped N+ region here and heavily doped N+ region here. And then we make contacts. We evaporate aluminum, we make contacts here. So this is called the source, this is called the drain, this is called the gate, and this is the body of the transistor. We call it the body here or substrate here. Okay, the substrate on which you are making the transistor. So this is body or substrate. So our MOSFET is a 4-terminal device. But for our sake, what we will consider most of the time is that the body, and which is true in most cases, that the body is connected or shorted to the source here. So body is at the same potential as source. So effectively it becomes a 3-terminal device then. So let's see how this particular device operates. So this is a simplified schematic of our transistor here, MOSFET here. So again, there is a gate, metal here, oxide here, P-type semiconductor here, N+ region source, N+ region here drain. So in this case, the source and the drain can be interchanged. So it's a symmetrical device. And note that because this is P-type here, the body is P-type here. So there's effectively a PN junction here. N plus P is a PN junction. And there's another PN junction here at this particular point here. And therefore, when we apply, let's say, a voltage, so we'll not bother about the body. We'll assume that body is at the same potential as source and connected to ground. So when you, so the only possibility of current that can flow is, obviously gate, no current can flow because it's an oxide. So gate current is 0. And body is shorted to source and no current flows in the body also. And the possibility of current is only between source and drain here. Okay. And but we see two diodes connected back to back. So when we apply 5 volt here, this particular diode will get reverse biased here, and therefore no current would flow. No current would flow because there's no path from the drain to the source here. There is no path, conducting path here. And no matter what you apply, at least one of these diodes will be reverse biased, and therefore the current will not flow here. So 0 current. But then things become interesting. So let's see, things become interesting when you apply voltage to the gate here. So I've drawn a P-type semiconductor here. So P-type semiconductor will have all these ionized acceptor atoms here in circled minus sign there. And plus sign denotes all the holes that are there here. Again, the acceptor atoms are immobile. The holes are, of course, they can move around. And so there are a lot of holes here, maybe, and maybe very few electrons. So one is shown, maybe 1 electron here. This is a ionized acceptor atom, so electron is not even shown anyway. All right, so when we apply a positive voltage here, so this positive voltage, note that what it will do is, this positive voltage will create a field down pointing into the semiconductor and will push away the holes. The holes are mobile and they'll react to the field here and will push away the holes here. And the positive charge will go and will eventually, positive charge will come and sit over here. Okay, positive charge will come over here. And so this region will be depleted of holes that is there here, and you create a depletion region because the positive charge has been pushed away and removed to the gate. And so this region becomes charged. It leaves behind the ionized acceptor atoms here, negatively charged. So 0.2 volt, and so this is a simplified view. It doesn't mean all the holes have been pushed away, but just shows that a lot of holes have been pushed away from the surface, and they've been positive charge has been put at the gate here. So depletion region is formed here. Now if you apply a higher voltage 0.4, the field will become even stronger, even more holes will be removed, and so depletion region will widen. Right, depletion region will widen. But something interesting occurs here. So depletion width increases because more and more holes have been removed from close to the surface here, and the positive charge is put over here. But something interesting occurs here. And the interesting thing is that the electron density at the surface increases. So note that holes have been pushed away from here, but electrons, if there are any electrons, the positive field will attract the electrons to the surface here. But electrons increase at the surface here. And that's because of this fundamental relationship that N into P is Ni squared. So when we reduce holes from a particular place, if we make P smaller, the right hand side is a constant, so N increases here. So the number of electrons, they start increasing. So that makes things interesting here. And at a sufficiently large voltage, which we call as the threshold voltage, you create lots of electrons at the surface here. Lots of electrons at the surface, and therefore you create what we call as a sheet of electrons. A sheet of electrons, and that connects the two source and drain regions here through another region of electrons itself here. Okay, so this is all this depletion charge there. And note that this sheet of electrons that we create, we also call it an inversion layer. Because a normal p-type semiconductor, in a p-type semiconductor, the number of holes are much larger than number of electrons. But at the surface, if you apply a sufficiently large voltage, what you have done is you have created a layer where number of electrons is much larger than number of holes, because all the holes have been pushed away and number of electrons have increased. So number of electrons is much larger than number of holes. So you have inverted the polarity. It was p-type, but you have made the surface n-type, and that's why it's called the inversion layer, this sheet of electrons. So let's look at this process in a little bit more detail. Okay, so we are only showing you this part here. I'm not showing the n plus part here, this part of the region here. And so this is there. And for the sake of discussion, let's assume that the initial doping of the p-type is 10 to the power 16, and therefore the initial number of electrons is Ni squared over p, about 10 to the power 4. So very few electrons, mostly holes here. So now we are going to apply the gate voltage, more and more positive gate voltage. So what it will do is it will push the holes away, and the hole density at the surface will keep on going down. So that's what we are doing here. So we are looking at the surface itself. We're just trying to concentrate at the surface what happens here. And so note that positive voltage will push the holes away, and the hole concentration at the surface will go down. So what we are saying is, as what you start from Vg equal to 0, and you start increasing Vg, starting from 0 to 0.1 to 0.2 and all that, and you keep on increasing Vg here. So that's the arrow. So as you increase Vg, you create more and more electric field pointing downwards, and therefore you push more and more increasing amount of holes away from the surface. So what happens is the hole density at the surface, which was initially 10 per 16, because the doping was 10 per 16, the hole density starts from 10 per 16, but then goes to 10 per 15, 14, 13, 12, 11. It starts to decrease as we apply higher and higher value of Vg. But note that as Ps is decreasing, Ns has to increase, because the ratio product Ns into Ps is Ni squared. So it starts from 10 to the power 4, 10 to the power 5. So at this point, the whole region is p-type. The surface is p-type. P is greater than n. But then as you keep on applying gate voltage here, eventually Ps becomes 10 to the power 10, which is the intrinsic carrier concentration, and Ns also becomes 10 to the power 10. At this point, you have made the surface intrinsic, because both P and N are equal to each other. So it's like an intrinsic semiconductor. If you apply even higher field, the hole density then becomes, instead of 10 per 10, 10 to the power 9, 8, 7, 6, 5, and the electron density becomes 11, 12, 13, 14, and all that. Now note that electron density is higher than hole density. So the surface, we say, is inverted. It's no longer p-type, but the surface is like n-type with electron density higher than p-type. Eventually, if you apply sufficiently large voltage here, what happens is the electron density at the surface becomes really high. For example, 10 to the power 16. Note our doping was 10 power 16 and the electron density has become 10 power 16. So when the electron density here becomes 10 power 16, which is same as the starting hole density at the surface, we say we are entering a strong inversion region here. And now we have created lots of electrons at the surface. So we create a sheet of electrons, and the source and the drain region, which were n-type, they get connected by this sheet of electrons here. So we call this a strong inversion region here. And at that point where the surface electron density is the same as initial hole density or initial doping that was there here, we call that point as the threshold point here. Right. And so at that point, the surface is strongly n-type, and one could expect the significant current would start flowing here. So this is what we are talking about. As we keep on applying the gate voltage here, the hole density keeps on reducing and the electron density keeps on increasing here. And eventually the electron density crosses this Na part here, and this is what we call as the threshold point here. So when gate voltage is larger than the threshold voltage, what we have is a sheet of electrons at the surface here. Okay. And if you apply even higher gate voltage, you'll get even larger sheet of electrons here. Right, so a lot more electrons at the surface here. Okay, so that's the, so we'll see further what happens, but this is the symbol that we use for our MOSFET here. So it is, as we said, it is a 4-terminal device, drain, gate, and source. It's connected through a dotted line because normally, see, if you don't apply a gate voltage, there is no path from source to drain for current to flow. We saw that there were two back-to-back diodes here. That's why this broken line here, okay? So that's the symbol here. And this is a simplified symbol for this one here, where body is connected to the source here, body and source, and the arrow is pointing out like this here to show an n-type behavior here. So this is an n-channel MOSFET here. And sometimes you will see that the body contact is not made here, but the body contact is made at the top. So when you create a P+ layer, you're effectively connecting to the body here. All right, so this is the behavior here. So what happens is there is a sheet of electrons at the surface here. Why are we calling it sheet of electrons? Because the electrons are kept at the surface due to the electrostatic field which points downwards here. So all the electrons reside practically in a very thin layer at the surface itself. So you can think of it now like a capacitor here. One plate of the capacitor is metal is here, the other plate is this sheet of electrons. And so this inversion charge, how much inversion charge is there, will be equal to the oxide capacitance. So this is capacitance per unit area. And this is the inversion charge per unit area. So oxide capacitance multiplied by VGS minus VTHN. Why VTHN? Because it's only when the gate voltage exceeds VTHN that we get this inversion layer here. And when gate voltage is less than the threshold voltage, there are electrons at the surface, but the electrons are very small in concentration. So there's an inversion charge density which is equal to capacitance. Note that capacitance is capacitance per unit area multiplied by VGS minus VTH. So we can calculate how much inversion charge is there using this relationship if we know the value of threshold voltage. Now, when you apply a voltage, so we want to make a transistor out of it. So what we have done is we have applied a gate voltage and we have created an inversion layer here. Now let's apply a voltage between source and drain here. So let's apply a positive voltage here, 0.5. So when you apply 0.5 volt here, of course, the electrons will flow from source to drain here. Now there is a path because this is N+. The surface is also N-type is here because a lot of electrons are here, and this is N+. So there's a path here and the current would begin to flow. But the other thing that begins to happen is if you apply 0.5 volt here, then at this point, the voltage in the channel, so this is what this the layer of inversion layer, we call it a channel. And we call it a source and we call it a drain. So it's like water flowing from source to the drain via the channel. Okay, so the voltage in the channel at this particular point would be practically equal to 0. While the voltage at this particular point in the channel would be practically equal to 0.5. Note that N+ layer is very low resistance. So you can think of this as being connected to the terminal here and this being connected to the terminal here. So this is 0 and this is 0.5. So the voltage along the channel will vary. Here it will be 0.5, somewhere will be 0.4, somewhere will be 0.3, 2, 1, and eventually 0 here. So the charge, inversion charge in the channel will also vary because we said it's a capacitor here. At each point there's a capacitor. So charge anywhere in the channel will be Cox, VGS minus VTHN minus Vx, the potential at that particular point here. Okay. So the amount of charge in the channel will keep on changing. So there are different amounts of charge at different places in the channel. So as you apply 0.5 volts or a positive voltage here, current begins to flow, but the nature of the channel also alters. And so note what happens here. When you have 0 and 0 here, no current flows and the channel is uniform. Note that the channel is pretty thin, is just shown for sake of clarity with a certain thickness here. So the channel is uniform throughout. But when you apply 0.5 volt here, the channel narrows here. Why? Because narrows here to show that there's less amount of inversion charge. Because inversion charge, remember, inversion charge was given by Cox, VGS minus VTHN minus Vx. So higher potential is here, positive potential, and therefore the charge is smaller here. At this point, the potential is lower, so the charge is higher. At this point, the potential always remains 0, so the charge stays as Cox, VGS minus VTHN. So as you apply a positive voltage here, the charge in the channel, in general, the charge in the channel reduces, and therefore the resistance of this particular path, it reduces here. And as the resistance reduces, the current I versus V, the drain current versus the drain voltage, starts bending here. If it were a perfect resistor, it would have been a straight line. It would have been a straight line like this here. But because the resistance value, R channel, IDS equal to VDS by R channel, so MOSFET acts basically like a resistor, a nonlinear kind of a resistor. And the current is the voltage divided by, in a very simple picture, voltage divided by the resistance here. And as you apply a positive voltage, the charge in the channel is reducing, and that's why the resistance is increasing. And so the curve starts bending. Eventually, a stage is reached where the current actually becomes independent of drain voltage here. We call this point as the saturation. The drain current has saturated. This voltage as VD sat, and it can be shown. So this is called the saturation region, obviously, because the drain current is saturated. We call this the linear region. Although it's not linear all over, it starts off with a linear variation here. We call it the linear region or the triode region here. Triode region in analogy with the vacuum-based triode tube here. And we can show here that VD sat is equal to VGS minus VTHN here. All right, so let's look at it in a little bit more detail here. So as we keep on applying higher and higher voltage, so for the sake of discussion, let's suppose VGS is 2 volt, threshold voltage, let's take it as 1 volt, and Vx is the potential anywhere in the channel. So when you apply a higher and higher drain voltage, you reach a point here where the amount of inversion charge becomes negligible here. Note that Q inversion is Cox, VGS minus VTHN minus Vx. So when you apply 1 volt here, the channel voltage is 1 volt. So you have 1 here, and VGS is 2. So this becomes practically equal to 0. So we say we have created a pinch-off region here. We have pinched off the channel here. Okay. Now, actually what happens is the inversion, this relationship starts to break down when you make inversion charge very small. What you have done is you've created a region with very low amounts of inversion charge or a very high resistance region here. And when this happens, the current begins to saturate. And to understand in a very simple way why the current saturates this, let's look at this picture here. When you have very low voltage or 0 voltage applied to the drain here, then the channel is uniform. And when the channel is uniform, you can think of it being made up of, let's say, a small set of resistors like this here, a distributed resistors like this. If you change the drain voltage by a certain amount, delta VD here, obviously the delta VD, the drain voltage, let's say if I increase it by 0.5, it will distribute equally over all of these resistors here. And a fraction of the applied voltage will appear across this R here, and the current would increase. But now look at this situation here. When you have applied 1 volt, the inversion charge is different at different places. And the inversion charge has gone to very, very small values here. So now the resistors that were uniform all over, now the resistor, let's say, is R, just like R here, but then the resistor would start increasing. And it would become really high because the inversion charge is negligible somewhere here. Now if I apply a drain voltage, if I increase the drain voltage by a certain amount, note that almost the entire voltage will drop here and very little voltage will go here. So if you increase the voltage here, and if there is no increase in voltage across this particular element here, that practically means that no increase in current occurs here. So that's why we see saturation here. So saturation occurs when we create a pinch off, a high resistance region here. And so the drain current versus drain to source voltage starts to saturate here. And note that now something interesting occurs. So once I'm in this particular region, if I change my drain voltage, if I go from 1 to 2 volt, well, it doesn't do anything to because this region is very high resistance region here. So as you go from 1 to 1.5 or 2, all the voltage is dropped here. Nothing happens to the current that flows from here to here. No change in voltage occurs in this region here, and therefore the current also doesn't change. And so the current is not sensitive to the drain voltage at all in this particular region, obviously, because it has, you can see here, it's saturated. But the current is very sensitive to this voltage. If I change from 2 to 3 volt, the amount of inversion charge would increase and the current would also increase. So effectively what we have done is we have drain to source current, which is very sensitive to gate to source voltage, but is not sensitive to drain to source voltage when you are here in this particular region. So you get transistor action here. Okay, so as summary, we have two transistors, bipolar transistor here, where the output collector current changes with base emitter voltage in an exponential manner here. The output collector current versus VCE changes in this particular manner here. And this is the important part of the characteristics, where the current output current is insensitive to output voltage here, but very sensitive to input voltage here. And this is the MOSFET here. Two very different structures, but sort of similar characteristics that you can see here. This is the output current versus output voltage characteristics here. Again, this is the important part here, where the drain current is not sensitive to the drain voltage, but the drain current is very sensitive to the gate voltage here. So drain current versus gate voltage sensitivity is there. All right, and we saw earlier that these are not ideal transistor characteristics, but if we bias a transistor here and somewhere here, similarly we bias a transistor here or somewhere here, then by the methodology that we had discussed earlier, we can build amplifiers. So all that we need to do is, we took that hypothetical element called Z in the last lecture. We can take this out and substitute by a transistor, bipolar or a MOSFET, and our amplifier would work and amplify the signal that is shown over here. All right, so let's stop here.